Yes, sir. Right, sir. Road junction at checkpoint Lima. Yes, sir. Can have a helicopter there in 20 minutes or less. Yes, sir. Watson? Take 0241 CO. Bring him up to this bridge so he can check the condition of it and its approaches. On the way up, follow the river so he can locate any other bridge sites or fords he can use in the event this bridge is destroyed. Any questions?
No, sir.
In combat, that's all you'll get. A few brief words describing your mission. The rest is up to you. Plan your flight, prepare your map, select checkpoints, calculate fuel requirements, and be there in 20 minutes or less. Right now, in primary flight training, is when you must learn how to do it. Later in your training, you'll get many hours of practice in flying such problems. Let's go back several years in this aviator's career to the days when he was in primary. Watson is a little worried about this part of flight training, navigation. It sounds, well, sort of complicated. Physical things like flying are hard enough, but charts and plotters and computers, there always has to be something to make life more difficult. But the very first thing the instructor says makes Watson determined to learn navigation.
During the past few years, almost the entire world has been equipped with electronic aids to navigation. Range stations, marker beacons, ADF facilities, omni-range, and radar. We could eliminate dead reckoning navigation and pilotage from your training, except for two exceedingly important facts. First, in the low-level tactical flying you will be doing as Army aviators, you can make very little use of these electronic aids. Second, if a major war were declared tomorrow, these commercial electronic highways might very well be shut down for the duration. As Army aviators, therefore, pilotage and dead reckoning are more important to you than to most other aviators. Setting it down in a pasture because you're lost and out of fuel is embarrassing in peacetime. In combat, it could be fatal.
With a new understanding of the importance of navigation, Watson is ready to learn, and he soon makes a pleasant discovery. There isn't as much math and mystery to navigation as he had feared. Common sense is the main ingredient, and Watson, like most men selected for flight training, is long on common sense. Most military men understand the basic principles of geography. The use of latitude and longitude to define position isn't difficult, but it's a little harder to understand how the features on the spherical surface of the Earth can be transferred to a flat sheet of paper, like a map, without a great deal of distortion. This is accomplished by a process called projection. The three most important projection techniques are Lambert conformal, Mercator, and stereographic. Each of these methods of projection has special characteristics. For example, Mercator projections are best suited for use near the equator. Charts based on stereographic projections are most accurate and easiest to use in the high latitudes, near the poles. But Lambert conformal projections give the aviator the truest representation of terrain, direction, and distance in most areas of the Earth. Therefore, Lambert charts are most frequently used for aerial navigation. Map reading was not new to Watson, but he had to change his concept of the length of a mile. For years, he'd thought in just plain miles or statute miles. In the United States, a statute mile is 5,280 feet, but in other countries, it has different lengths. The nautical mile, however, is the same all over the world. It is longer than a statute mile, but its length in feet is not important. The important and very handy fact about a nautical mile is that it equals 1 minute of latitude. Therefore, each degree of latitude always equals 60 nautical miles. This makes rapid guesstimating of distance very simple. For example, these two airfields are just about 1.5 degrees of latitude apart, or approximately 90 nautical miles. Remember, you can always measure nautical miles on any chart, even if you don't have a nautical mile scale, because 1 nautical mile equals 1 minute of latitude. Watson learned to respect charts. Every flight depends on the picture of areas, locations, distances, directions, and conditions which they provide for the aviator. Having learned about the charts available to aviators, Watson started on a new phase of his course in navigation, plotting and measuring, the technique used for laying out a course and determining its distance and direction. At first it seemed that the instructor was making a great deal of fuss about flying from A to B, but it turned out to be more complicated than Watson had expected. Learning how to use a plotter was simple. It has a straight edge for drawing lines and scales for measuring distance on various charts. It also has special scales for determining the direction of course lines. Step one in plotting is to draw a course line from departure to destination. Then measure its length with the appropriate scale. Determining the direction of the course line is equally simple, provided one precaution is taken. Every line has two directions, in this case about 075 degrees and 255 degrees. Aviators have been known to use the opposite direction and fly a fine course directly away from their destination. To avoid this error, estimate your direction first. This direction is obviously in the quadrant between 0 and 90 degrees. Now place the straight edge of the plotter on the course line and slide it until the hole at the center of the direction scale is over a meridian nearest the midpoint of the course line. Where the meridian intersects the arc of the scales, read the scale which gives the figure in the estimated quadrant between 0 and 90 degrees. The direction of the course line is 075 degrees. Since we estimated it first, we know that it certainly is not 255 degrees. The direction of the course line measured from the meridian is called true course. It would be very nice if we could simply point our nose to a true course of 075 degrees, fly at 60 knots, and 1 hour later arrive at point B. But we can't always do this because of wind effect. Let's say there is a wind from 320 degrees at 20 knots. During our hour of flight, the wind would drift us 20 miles to the southeast, and we'd arrive at point C at the end of the hour rather than at point B. How do we correct for this drift? Actually, the answer is here on the sketch. During flight planning, we construct a wind triangle based on the factors we already know, and solve for this angle. Let's call it X degrees. Now, by applying this X degrees in the upwind direction from our course, we obtain a new direction called heading. This angle is called true heading. In other words, we turn the nose of our helicopter X degrees upwind so that we are flying into the wind and overcoming the drifting effect as we make good our course to point B. The ability to obtain drift correction quickly and accurately depends on learning to solve wind triangles, and that means learning to work with the computer. On the wind face of the computer, you can work any vector problem which may come up, either in flight planning or in the air. Practice until you're thoroughly familiar with it. The slide rule face of the computer is equally important. Its major use is in the solution of problems concerning time, speed, and distance. But it also can convert statute miles or kilometers to nautical miles, or give you the answer to any problems of multiplication or division. Set up a sample problem for which you know the answer. Working out that problem will show you how to work any similar problem. Now let's go back to our problem of flying from A to B. We have calculated drift and obtained a heading which will compensate for wind. But this heading will still not take us to point B. True course and true heading were measured from a meridian which points to the geographic North Pole, or true north. But a magnetic compass points to the magnetic North Pole, which is actually some distance away from the geographic pole. For this reason, at most points on the Earth, there is a difference between true north, shown by meridians, and magnetic north, indicated by a compass needle. This difference is called variation. The amount of variation you must apply to true heading to obtain magnetic heading is shown on charts by isogonic lines, which connect points of equal variation and show variation east or west between true north and magnetic north. By applying variation to true heading, we obtain magnetic heading. Another factor which affects your compass reading is the aircraft itself. Let's say this helicopter is heading straight toward magnetic north. It would seem that its compass should read due north, but it does not. The reason for this is that the magnets which actuate the compass are attracted by steel in the structure of the helicopter, and by electrical fields from its wiring, magnetos, and so forth. This error is called deviation. Near the aircraft compass, you will find a compass card, which gives the deviation for the compass in that particular aircraft. Deviation is usually quite small, but on a long flight it can be important. Applying deviation to magnetic heading will give you compass heading. Which is the heading you must fly to arrive at point B. Let's review to put together all of the steps. Starting with true course, which is measured from a meridian, we add or subtract drift correction. To obtain true heading. So far, we have taken care of the effect of wind on our flight. To true heading, we add or subtract variation. To obtain magnetic heading. Now we have taken care of the fact that the magnetic pole is not located at the geographic pole. To magnetic heading, we add or subtract deviation. And obtain compass heading. This accounts for the error induced in a compass by forces other than the magnetic pole. After completing flight training, Watson was assigned to Fort Hood. He's only been there a week or two, and right now he's receiving his first assignment for a cross-country flight. He's to fly a Sioux from Fort Hood to Fort Sill, leaving Hood at 1000 hours. Oh, 750 hours, just about 2 hours to get ready. Let's listen in on Watson's thoughts for a moment.
Maybe I should get someone to help me plan the flight. Someone with more experience. No, I'll do it myself. No time like the present to find out how much I learned in school.
Within 30 minutes, Watson is down at operations and has made a good start. He's checked weather and found that it's VFR all the way. And he's selected his charts and surveyed the route. Right now, he's estimating his fuel requirements and selecting refueling points. Let's listen in again.
Little better than 3.5 degrees of latitude. 3.5 degrees times 60 miles to the degree. 210 miles plus a little bit. 2 fuel stops should do it. One at Walters and one at Shepherd. Just close enough together to leave me a margin for error. Now I get the course lines drawn and select checkpoints.
After drawing in course lines, he proceeds to select checkpoints, making sure that they are obvious ones, not easily confused with similar points close to his course. Before recording them on his chart, he rechecks to make sure they are close enough together. He'll be flying at about 1,000 feet in an H-13. Within a few minutes, Watson scaled off the distance between checkpoints and recorded it on his charts. As he finished each leg, he checked his arithmetic by making sure that the individual distances added up to the total length of the leg. As he works with the plotter, he remembers his instructor saying,
"Always estimate direction first, then use the plotter. Make sure the arrow points the right way. Read from low numbers to high."
Using this error-proof procedure, Watson will obtain true course for each of the 3 legs. In a few minutes, Watson will call weather and get the wind at his selected altitude. With this information, he will work out drift correction and get the headings for each leg. With the aid of the computer, Watson has now obtained true airspeed, ground speed, drift correction, and true heading for each of the legs. And with this information, checks to find variation from the closest isogonic line. Variation remains the same for all 3 legs. Watson seems happy with the job of flight planning he's doing. From here on, Watson's flight plan is clear sailing. He'll finish with plenty of time to recheck his work, file a flight plan, and pre-flight the Sioux. Then, from the compass card in the helicopter, Watson will select the deviation appropriate for each leg of his flight. Applying deviation to magnetic heading, he will obtain compass heading and be ready to take off. Careful planning and practical experience such as this at Fort Hood will really pay off in this combat situation where we first met Watson. For combat missions demand an expert knowledge of map reading, dead reckoning, and pilotage. Course lines will follow stream beds or ravines, and checkpoints may be no more than 200 or 300 yards apart. Ability to stay oriented in low-level flight demands superior knowledge of all the principles of navigation. Armed with his thorough knowledge, Watson can and will undertake and complete this mission successfully.